Okay, hey everyone. We're looking at lesson 4. We're going to be solving different logarithmic and exponential equations today. Um, well, let's give it a go. Here we're starting off with, the old-fashioned way of solving for exponentials. The strategy here is if we can convert to the left and right side to have the same base for our power, then we know the exponents must be equal to each other. So our strategy is to find a nice base to play nice with both sides. So here, between a 4 and a 16, 4 will suffice. We'll keep the 4 the same here. And we should express the 16 as a base of 4. So that's 4 squared instead. And let's bring that 4 upstairs. So we'll change the sign on that 2 to be 4 to the negative 2. And now that we have the same base on both sides, we can let the exponents equal each other. We'll see that 2x is equal to negative 2. And we're going to get that x is equal to negative 1. One word problem we saw together in grade 11 was the half-life equation. The mass remaining after a initial mass was decaying at a half-life rate of t over the half-life is given by this equation. So just a quick refresher. This is like your final. This is your initial. Since we're specifically talking half-life, that's a half there. Time. And then this in the bottom here is called the half-life period. How long do we have to wait for this thing to half itself? Okay, let's have a read. A radioactive material has a half-life of 40 days. Okay, that's our little lambda or h. Either one is good. If you begin with 20 milligrams, that's your initial beginning. How long will it take? So t is unknown. We want to solve for t. Before we only end up with 2.5 milligrams. That's our final mass m of t. Okay, let's give it a go. So we're looking at the final mass of 2.5 is equal to 20, the initial starting mass, 1/2 to the exponent of t divided by 40 days, which it takes to half itself. Okay, we're going to isolate for that t. First thing is we're going to divide both sides by that 20. What are we going to get? So that's 1 over 5, 1 over... Give me a second here. 5 we 1 over 4 is 1 over 8 is equal to 1/2 t o to the 40. And then 1/2 is better known as 1/2. Sorry, well, 1 over 8 is better known as 1/2 to the exponent of 3, which is 1/2 to the t over 40. And okay, now if we get lucky and these numbers play nice, we can make them the same power, the base on both sides. Now we see that 3 is equal to t over 40. We'll multiply both sides by 40. We'll get 120 is equal to t. Therefore, it takes 120 days for a 20 milligram sample to become 2.5 milligrams. Okay. All right. Perfect. Well, what if we don't have the luxury of that same base idea? Now, 50 is kind of nice, but we can express it as 2 times 25, which is 2 times 5 squared. However, we're kind of stuck with that 2 in the front. We don't get a clean base 5 equals base 5. There's like a 2 in front, and that changes everything. We are unable to use the old strategy of getting things to the same base. So here we're going to operate with the inverse function of exponentials, which are logs. So let's look at the strategy here. We want to isolate the power on one side and then rewrite the expression as a logarithm. So we'll hopefully get it to the form of y equals b to the x. And then the inverse operation is we're going to take the log base b of both sides. Well, the log base b of y, oops, this should be a y here, little typo, is equal to log base b of b to the x. And hopefully you recognize this property, inverse and function applying to each other, those cancel out. We're going to get x is equal to log base b of y, which was the statement up here. Okay, so in essence, let's kind of isolate things and then take the log. Grab your calculators. Here we go. Here we're set up in the format we like. Y is equal to some base to some exponent over there. Okay. No coefficients, nothing like that. Okay, so now we're going to take the log base 5 of both sides. Let's write it out. Log base 5 of 5 to the 2 minus x. In the future, you're going to skip this step. You're going to go directly to the next line. Okay, well, we'll handle this log, this log base 5 of 50 in a second. We'll grab a calculator. This part, we need to once again recognize that these are opposite operations. So we'll be left with only the input 2 minus x. And what do we see here? Well, now we can just strictly isolate for x. And by the way, this question could be keep your answer exact. And you would just do the following. We'll get negative x here equals to log base 5 of 50, and then minus 2. And then multiply everything by a negative 1. X is equal to 2 minus log base 5 of 50. And if you wanted to, you can stop here. This is an exact solution. If they ask for you to round, okay, now grab a calculator. Let me grab mine. It needs a little help here. We're going to go for 2 minus the log base 5. Just as a refresher, in case you don't have the fancy log button that specifies a base, you can still express this as log of 50 divided by the log of 5, which I'm going to do right now. So to take away the log of 50 all divided by the log of 5. And I'm getting my final answer as negative 0.43. Okay, one more time. We are going to first rearrange so we are in the format of a single number is equal to a single power, no coefficients on the power. Right now there's a coefficient on the power. Let's bring it to the other side. We're going to get to 2x over 3 is equal to 40 over 3. Now, how do we get rid of this base of 2? We need the inverse operation. The log base 2 of this and the log base 2 of this. Okay, let's see what happens. We get x over 3 is equal to the log base 2 of 40 divided by 3. We will multiply both sides by 3. X is equal to 3 times the log base 2 of 40 over 3. And to be honest, I am pretty satisfied. In case you are asked to round, let's give it a go. We're looking at the log of 40 divided by 3. And then we'll divide that by the log of 2, because that's base 2. And then we're going to multiply that final answer by the 3 what was in front. 11.21. Beautiful. Okay, let's keep going. All right, equations with more than one power with the same base. Okay, let's give it a shot. So put the powers on the same side of the equation, common factor the power from both sides, solve for x. Okay, little refresher. If you have x to the 10 plus x to the 8, these two can be common factored. What is the greatest power you can take out of both of them? Well, they both can give up to 8. Then we get the x to the 10 divided by x to the 8, we get x squared. And x to the 8 divided by x to the 8, well, that's just a 1. Now, that's the idea we want to carry forward here. Okay, so this 3 to the x, and there's 3 to the x plus 4. How many 3's in terms of the exponents can we take out? Well, this one has 4 more than this can give. So the most we can take out of both of them is just 3 to the x. I'm going to show it to you the long way around first. So we're going to take out the 3 to the x. That means we're dividing both things by 3 to the x here. Minus 3 to the x over 3 to the x is equal to 240 here. And what do we see now? Well, this becomes 3 to the x plus 4, take away x, the one in the denominator here. These are the same number, they become a 1. What is our final answer? Not final answer, sorry. The simplified form of this. And by the way, in the future, you're just going to go from here to here. You're going to write it as 3 to the 4, the x take away x cancels out the x's, minus 1 is equal to 240. And typically speaking, with these examples, you're just left with a number over. So what do we have here? 3 to the x, 3 to the 4 is 81, take away 1 is 80, is equal to 240. You're going to divide both sides by 80. You're going to get 3 to the x is equal to 3. Then obviously, x is equal to 1. Okay, one more time. What is the most we can take out of both of these exponents? We're going to take out the one which is lower. The one which is lower is this x minus 3 bit. Okay, once again, I'm going to go a little slow here. Once you get more comfortable with it, feel free to kind of go a little quicker. Well, I'll take out the lower power, 2 to the x minus 3. Well, that makes this one pretty easy. Well, if I divide it by itself, it's just the 1. Let's go a little slower with this piece here. 2 to the 2x plus 2 is being divided by 2 to the x minus 3. Okay, is equal to 31. One more time. 2 to the x minus 3. And here in this exponent, we had that original x plus 2 on top, so x plus 2. But because we were dividing or common factoring out this piece, we want to subtract that all out. That's what we're going to do. And minus 1 is equal to 31. Okay, we're getting there. 2 to the x minus 3. And let's clean up this exponent now. The x take away x, well, there are no more x's, plus 2. Subtract the negative 3 is actually a 5. Take away 1 is equal to 31. Okay, and then 2 to the exponent of 5 is actually 32. Take away 1. And oh, how nice of Mr. Wills. He has created a nicely solved equation. Okay, we're going to divide both sides by 31. We're going to get 2 to the x minus 3 is equal to 1. And now let's write this as an exponent of 2, which is a base of 2, which is 2 to the 0. So therefore, x minus 3 is equal to 0. Or in other words, x is equal to 3. And by the way, you're always more than welcome to take that in 3, put it up top, and see how it goes. So you know what? Let's do that in this case. So 2 to the 3 plus 2 minus 2 to the 3 minus 3. Let's see what happens. 2 to the 3 plus 2 is 5. That's 32. Take away 2 to the 0, which is 1. And yes, we do get the 31. The answer x equals to 3 checks out. Okay, here you're going to notice something slightly different. It's a little bit similar to what we saw before, but you're going to notice that before the coefficients on the x were the same. However, the coefficients in the x here have a different pattern to it. We have a 2x and an x. Here's a hint. We're going to make a let statement. We're going to say let 3 to the x equal a letter, k. Okay, well, that makes this one quite easy to swap out. That's minus 2k is equal to 3. Okay, how about this? Well, this is the same thing as saying 3 to the x all to the power of 2. So that's a k inside here. And then you have a squared here. Okay, what am I getting at here? When you see a pattern with a coefficient on the exponent for the x's, and you see that they are scaled by a factor of 2, you're eventually going to get a quadratic. That's the key to this type of question. Okay, let's bring the 3 over. We get k squared minus 2k minus 3 is equal to 0. Break out your favorite factoring technique. You're going to get something like k minus 3 and k plus 1 is equal to 0. And now we got to substitute back in what was k. K was that 3 to the x minus 3 is equal to 0. And then k was, once again, 3 to the x plus 1, which is equal to 0. We're going to move the 3 over. 3 to the x is equal to 3. Therefore, x is equal to 1. And to what exponent on the x can it equal negative 1? Turns out, does not exist. 3 to the x looks like this. And we're asked the question, when does a heat reach a height of negative 1? Turns out, never. Okay. Well, we'll apply our same logic, same trick over here. Let's give it a go. We're going to say let this phi to the x character equal a letter, t. And we'll make some substitutions. We'll get 8t squared plus 8t minus 6 is equal to 0. Let's common factor. 2 times 4t squared plus 4t minus 3 is equal to 0. Once again, we got a common factor, so I'm feeling a 2, 2 here. Yeah. by intuition. A minus plus 3 and a minus 1 works out quite nicely. We're going to get 2 times 2t minus 1 and 2t plus 3 is equal to 0. What's next? Okay, once again, maybe we'll put back our t's. T was originally that 5x, 5 to the x minus 1. And that, once again, 5 to the x plus 3. Okay, and we have to solve each of those factors there. Let's solve this factor first. So we have 2 times 5 to the x is equal to 1. I'll move the 1 over. Divide by 2, so we have 5 to the x is equal to a half. And unfortunately, this doesn't really have a nice answer. We are simply stuck with the log base of 5 of a half is our answer. If you'd like a decimal, please go ahead, grab a calculator, give it a shot. I'm going to leave it exact. We'll similarly solve this one. 2 to the 5 to the x plus 3 is equal to 0. So if we bring that over, we're going to get 5 to the x is equal to negative 3 over 2. And once again, we see this issue. We have a b to the x function equal to a negative number. Simply not in the cards. There's no value of x to make this happen. This thing has no solutions. No solutions. Actually, no solutions is the correct answer. Does not exist. No solutions. No solutions. No solons. Beautiful. Okay. And I think this is the last type of question we're going to look at today. Well, what if we have different powers altogether? And we have 2 of them. Well, our strategy will be to place the log, each power on one side. So put the powers on opposite sides. And then we're going to take the log of both sides, and you choose. You choose. You want to do just log x vanilla base 10? Or would you like to do log base with a bean? I'll show you both. Let's do just a simple log first. Okay. First, we are going to just get everything on one side. Put each power on one side. Okay. And now we're going to take the log of both sides. We're going to do log base 2 of x to the 1 is equal to the log, not base 2, of 3 to the x minus 1. And now we know a property. The exponent inside of a log can be re-expressed as the coefficient of the log. So we have an x plus 1 log of 2 is equal to x minus 1, the log of 3. Okay, let's do some distributive property here. We're going to get x log of 2 plus log of 2 is equal to x log of 3 minus log of 3. And we want to isolate for x. So let's collect all the x's onto one side. I'll bring it to the right side here. And I'll bring all the regular logs, these are simply numbers here. But if you want to keep them exact, we're going to leave them as log 2 and log 3. We're going to bring the log 2, log 3 over here. So we have log 2 plus log 3. I just added log 3 to both sides, which is equal to x log of 3 minus x log of 2 when I brought this log over to this side here. Now we can common factor the x's on the right there. We get x log of 3 minus the log of 2. And on the right, we are simply left with log 2 plus log 3. If you want, you may write that as log 6. And to be honest, we'll just finish off here. X is equal to the log base of 2, log of 6, divided by the log of 3 minus the log of 2. Now, it wouldn't be wrong for us to go a step further if you'd like. Call this log base 1.5. And I think at this point, we're going to call it. I don't believe this has a good answer. So let me just try it out just in case. We have the log of 6 divided by the log of 1.5. Yeah, not a clean answer. We're going to leave it right there. Okay, well, we did just the common log there, just regular log x. Well, our other option was to even be kind of a little better with how we chose our logs we're going to use. We can use an actual base here. wait a second. This one's a little bit nicer. You should spot something here. That 2 squared, that 4. We should get an exact answer here. We don't need to use the strategy of logs. Let's say you didn't see it. We'll do it anyway. Let's see. Okay, let's go with the we didn't see it first. So 2 to the 2x is equal to 4 to the x minus 1. We will now do the log base. Now you choose log base 2 or log base 4. There really isn't a wrong answer. I'm going to go with a log base of 2 here. Of 2 to the 2x is equal to log base 2 of 4 to the x minus 1. Every coefficient inside of a log can be expressed as a, exponent. I said that in the opposite way that I wanted to. Oh well. And then we get x minus 1 log base 2 of 4. Wait a second, log base 2 of 2 is actually all just a 1. So we get 2x is equal to this x minus 1 log base 2 of 4. I'm hoping you're also going to see that this has a nice answer. But let's say we didn't. We get 2x is equal to x times log base 2 of 4 minus 1. Well, sorry, log base 2 of 4. And we'll bring all the x's to one side. We have 2x, take away x log base 2 of 4 is equal to log base 2 of 4. Common factor the x's out. We get 2 minus log base 2 of 4 is equal to log base 2 of 4. This thing has no answers. Okay. I need a little bit more space here to talk about this one. The issue I'm encountering is here. And I'm going to explain this in a couple ways. Well, one, plug into your calculator. You're going to get x is equal to the log base 2 of 4 over the bottom 2 minus log base 2 of 4. But unfortunately, that's all 0 in the bottom. Because it's 0 in the denominator there, this coefficient 0, there's no solution here. Okay, I should have seen this earlier. Look at this. In fact, I was kind of alluding to it. 2 to the 2x is actually equal to 4 to the x minus 4 to the x minus 1 is equal to 0. Why is this an issue? Okay, let's draw this one over here. This one is, let's say, 4 to the x. What is the graph of this thing over here? We're subtracting off 4 to the x minus 1, a graph slightly shifted to the right. Turns out there's going to be no point of intersection because what are we looking for? We're looking for when these two things have a distance of 0, meaning they're meeting. Turns out that does not happen here. So part B, no solution. Okay, let's have a look here. Here we're going to break out the log trick and we're actually going to get an answer. These two did not play nice, even though it might look like they could. They don't. Okay, so let's give it a go. So 3 to the 2x is equal to 6x. Okay, let's break out the log base 3. 3 to the x is equal to log base 3 of 6 to the x. 2x. Okay, the left side, well, these two are opposite operations. We're left with 2x is equal to, there's no nice answer here. It's just simply log base 3 of 6 to the 6 right now. We'll bring the log base 3 to the x over to the left side. So we have 2x minus x log base 3 of 6 is equal to 1. And this thing here also has no solutions. Okay, for a different reason. Okay, let's common factor it. X common factored out of 2 minus log base 3 of 6 is equal to 1. X is equal to 1. Actually, no. Never mind. No, I got an answer. What am I saying? Okay, log base 3 of 6. That's it. Done. We found an exact answer. Why was I skeptical at first? No, I must have missed something. Anyways, so that's it. We found the answer. By the way, we use the log base 3 here, so we could cleanly remove the log base 3 of 3 we encounter on the left side here, it's more than fine to just leave everything as just log base 10, even though there's no base of 10 to turn around. Okay. Best of luck with the homework. See you tomorrow.